how do we analyze the running time of a recursive algorithm? The short answer is we need to solve the recurrence of its running time. So welcome to this video on solving recurrences. We're going to see several techniques, the master theorem, how to expand a recursion, how to analyze a recursion tree, and finally the substitution method. So let's first look at some standard recursive algorithms. The first one is binary search, recursive binary search. So what does binary search do again? So we are looking for an element x in a sorted array A, and we do so by looking at the middle element. If that is x, we're happy. Otherwise, depending on whether that is smaller or larger than x, we know, because the array is sorted, that we either need to go to the left or right. And that's binary search. What is the running time of binary search? Let's simply, as always, go through it line by line. So we have this first line here, which is a case if p larger r, that's the base of the recursion. That is a case where there's no array left. In that case, if there's no sub-array left, we know that the element is not there. We can report not found, and the running time of that is constant, so O of 1. Otherwise, we take the middle element, or the index of the middle element q. The middle element is in A of q. We compare it to x. That as such also takes constant time. But now comes the tricky part. The tricky part is that we're now going to recursively call the algorithm either on the left half or on the right half. So those are these two recursive calls. Now we don't know how long those take because we wanted to find out how long recursive binary search takes. So we want to analyze the running time of recursive binary search, but for that we need to know the running time of recursive binary search. But luckily we only need to know it on a smaller array or smaller sub-array, because what is happening here. So let's denote the running time of this algorithm on a sub-array of length n as t of n. Yes, and the length is determined here by p and r, so the length would be r minus p plus 1. So the running time on a subarray of length n is all of this plus the time for the recursive call. Now the recursive call, we don't know how long the recursive call takes, but we can express it in terms of t, because if t of n is the running time on a subarray of length n, and the recursive call is on a subarray of length n half, more or less, then we can write it as t of n half. In this case, rounded down, possibly minus 1. That is not that important. So essentially, the recursive call takes t of n half time. This leads to a recurrence. So recursive binary search obviously is a recursive algorithm. When we want to analyze the running time, we get a recurrence. And the recurrence looks as follows. We have the base case and then the recursive case. So if no elements are left, we're taking constant time. So t of n is O of 1 on a subarray of length 0. Otherwise, the running time is t of n half plus a constant. So this is the recurrence of binary search. It does not yet tell us how fast binary search is. And that's why we need to have techniques to solve recurrences. So let's just look at this recurrence a bit more and also a bit about some conventions. So very often we do not explicitly write down the base case. So this case O of 1 is often omitted because we simply assume there is a suitable base case for small n, which is simply O of 1. Also, this part here is often written without the rounding. Here I already kind of simplified slightly because there could have been a minus 1. So this we simply write as t of n half. That means the binary search recurrence, as we would write it down, is the following. T of n is t of n half plus theta of 1. We're going to see later in the video what this solves to. So we want to have something of the form, this is a function of n. So they replace this by simply a function of n. and we're going to see how that is done. But let's first take yet another example, and that is MergeSort. So as a reminder, MergeSort, we wanted to sort n elements, and we do so by splitting the array in two, recursively sorting each half, and then merging the two sorted arrays. What is the running time? Again, we go through it line by line. So there's the base case, and the base case again takes constant time. That is, if only one element is left, there's nothing that needs sorting, we're done. Otherwise, we split the array into two halves. So first of all, we define these variables n1 and n2. That as such, defining variables just takes constant time. Now we're copying the first half of A to A1 and the second half of A to an array A2, both of half the size. That takes linear time, because for copying I have to take every element and move it to the new array. So I'm overall moving n elements here. Finally, we have the merge. So the merge takes linear time because we were looking at the smallest element of the two subarrays, and the smaller one we add to our solution and then move to the next one there, and in that way we see we in every step move one of the elements to our final solution, and this takes linear time. So the merge takes linear time, but again we're stuck with the recursive calls. So we want to analyze the running time of MergeSort, but as part of that running time we get the running time of MergeSort, but now on smaller inputs. Because again, if we write the running time of MergeSort for n numbers as t of n, now what we're doing here in MergeSort A1 is that we're calling the algorithm now not on n elements, but on n1 elements, and n1 was n half rounded down. And here again, we're calling it on n half rounded up elements. So the running time here for line 7 will be t of n half rounded down for the sorting A1 and t of n half rounded up for sorting A2. So again, MergeSort is a recursive algorithm. We get a recurrence. We will need to solve this recurrence. But let me look at this just as we did for binary search once more. So this will be the recurrence for MergeSort. It takes constant time if there's only one element left. Otherwise, we get this expression, linear plus the two recursive calls. Again, we like to omit the base case, and then we also don't need to keep track of whether we're rounding up or down, which means we have t of n half plus t of n half, and this will be often written as simply 2 times t of n half. So the MergeSort recurrence is t of n is 2 times t of n half plus theta of n. And again, we have to figure out how do we solve this. So we're going to see techniques for solving recurrences next. Let's wrap up this first part with a quick quiz and a simple recursive algorithm, namely the algorithm for computing factorial. So we assume we have as input a positive integer, and if it's 1, we return 1, otherwise we return n times factorial of n minus 1. What we want to know is the running time of this algorithm, or more specifically, the recurrence of the running time. Now we're expressing the running time in terms of n. N is not the input size in this case, but it's simply the number that we get as an input, but still we can solve the recurrence in terms of n. And what do we get? Is it A, B, or C? So is it t of n half plus theta of n minus 1, or is it n times t of n minus 1, or is it t of n minus 1 plus theta of 1? It is t of n minus 1 plus theta of 1. The reason simply being we have the base case here, which takes constant time, and otherwise, if we call the running time for an input n, t of n, then here we're calling the algorithm on the input n minus 1. Let's look at some techniques to solve recurrences. So the easiest technique, or at least the easiest to apply, is the master theorem. So if the master theorem applies, it's kind of black box. It gives you the solution to the recurrence, and you're done. It doesn't always apply, so we also need alternatives. One way to solve a recurrence is to analyze the recursion tree of that recurrence, and that gives you a solution. It also gives you more intuition about why the solution is what it is. If none of this works, we can go brute force, and that means we're going to guess the recurrence and then use induction to show that it actually holds. And that's called substitution method. This, of course, requires us also to guess what the recurrence might be, and we can do so either by drawing some recursion tree without fully analyzing it, or by simply expanding the recursion, and we're going to look at what that means also. So let's start with the master theorem. So what is the master theorem? The master theorem applies to recurrences of the following form. T of n is a times t of n divided by b plus f of n. Both the binary search and the merge sort recurrence follow this pattern. So for binary search, we had t of n half, so there a is 1, b is 2, plus a constant. F of n is a constant. For merge sort, we had two recursive calls, so a was 2, both on half the size, so b was also 2, and f of n was linear, because we had to copy and we had to merge. So for both of these, we get this form. And for both, we will actually be able to use the master theorem. So that is a recurrence, or the form of the recurrence that we need to have. It can be rounded up or down. That doesn't matter. Now we get the following. If f of n is small compared to n to the log a base b, and small or grows slowly means that it is of order this minus epsilon in the exponent for some epsilon larger than 0. Then, as running time, we get this log n to the log a base b. If f of n and this n to the log a base b term have the same growth rate, then we actually get this term, so n to the log a base b, with an extra log factor. Finally, if f of n grows faster, or what we actually need is that it's an omega of n to the log a base b plus an epsilon in that exponent, then f of n is in theta of f of n, but we need this extra condition which we call regularity condition, and that is that there is a constant c such that a times f of n divided by b can be bounded by c times f of n. So this is the master theorem. In a moment we're going to see it in action. Just let me remind you, we have a notebook on this, so that is a bit of a step-by-step guide which tells you what to do if you want to apply the master theorem. It's fairly straightforward. I mean, you're looking for what is a, what is b, what is f of n, you're going to compute log a base b, and so on. But I mean, it's really, with a master theorem, you can really solve recurrences cookbook style, assuming that they fit this pattern. Should also say that even if you have a recurrence of this form, it does not immediately mean that you can solve it with the master theorem. So you could have that form and it doesn't fall in one of the three cases that we saw. If that's the case, bad luck, then we will use recursion trees instead. But now let's have a look at an example. So let's say t of n is 4 times t of n half plus n cubed. We have to look for a, b, and f of n. So a is 4, b is 2, f of n is n cubed. Now we need to compute log of a base b. So a was 4. The logarithm of 4 to the base 2 is 2. Well, because 2 to the 2 is 4. Now we want to compare n cubed with n to the log a base b. So this will be comparing n cubed to n squared. So we immediately see that n cubed is the larger of the two. And what does that mean? It means we're in the third case. We have that f of n is an omega of n to the log a base b, which is 2 plus epsilon. To prove that we're in that case, first of all, we need to give some suitable epsilon. But as epsilon, we can pick 1 here. So epsilon has to be positive, and 1 is the largest choice that we could take. Of course, 1/2 would also work here, but 1 is somewhat the natural choice because it's simply the one that fits. But 1/2 or 0.1 would also be correct. It would be just a bit arbitrary. 1 works nicely. Additionally, we need to check the regularity condition. So what was that again? We needed to check that a times f of n divided by b can be bounded by c times f of n for some c smaller than 1. So picking c as 1/2, we get the following. A times f of n divided by b is 4, because that's a, n divided by 2, because b is 2, cubed. Now if we do the calculation, this is 4 times n cubed divided by 2 cubed. 4 divided by 2 cubed, 2 cubed is 8, so that is 1/2. So we have n cubed divided by 2, which is c times f of n, because we picked c as 1/2. C is smaller than 1, so we have checked the regularity condition. Case 3 applies, so we can conclude that t of n is in theta of f of n, so t of n is in theta of n cubed. So let's solve some recurrences, starting with the following one. T of n is 2 times t of n half plus theta of n squared. So which case of the master theorem are we in? Case 1, 2, or 3? And what does this recurrence solve to? We are in case 3, and therefore the recurrence solves to t of n is theta of f of n, which means it solves to t of n is theta of n squared. So why are we in case 3? Because, and now it's just cookbook, a is 2, b is 2, log a base b is log 2 of 2, so log 2 of 2 base 2 is simply 1, meaning we're comparing n to the 1 with f of n with n squared. Now, n squared clearly grows faster, also by some epsilon that we can squeeze in between. So in particular, if we pick epsilon as 1, then n squared is in omega of n to the 1 plus epsilon, so 1 being log a base b. So we are in case 3 if the regularity condition holds. So for the regularity condition, we need to write down a of n to the f of n divided by b. This is 2 times n divided by 2 squared. Now, n divided by 2 squared is n squared divided by 2 squared. So this is 2 times n squared divided by 2 squared, meaning this is n squared divided by 2. This is f of, this can be bounded by c times f of n if we pick c as 1/2, which is smaller than 1, so we are fine, and case 3 applies. Next one. T of n is 4 times t of n half plus theta of n. Which case and what does it solve to? We are in case 1, and in case 1 it solves to theta of n to the log a base b, which in this case a is 4, b is 2, so log 4 base 2 is 2, so it solves also to theta of n squared. And why are we in case 1? Because f of n is of order n. We already said that log a base b is log 4 base 2, which is 2, so I'm comparing n, which is n to the 1, with n squared. Just as in the previous case, we can fit in an epsilon, in this case again of 1, so we have that n is an O of n squared minus epsilon, yes, and that is enough to be in case 1, and that is enough to get this solution. One more, t of n is 9 times t of n divided by 3 plus theta of n squared. Which case and what does it solve to? Okay, no surprise if I have 3 examples, this one should be case 2. And if it's case 2, we get theta of n to the log a base b times log n. So the solution will be n squared times log n. Once more, why is this the case? We have to find what a is, which is 9. We need to find what b is, which is 3. Now log of 9 base 3 is 2, because 3 squared is 9. Meaning we're comparing n squared, so n to the log a base b, with n squared. Both have the same growth rate. I mean, they're the same. So we're in case 2, and we get this extra log factor. So much about the master theorem. Again, if it applies, use it. And if not, for that case, we see more techniques next. So let's talk about what it means to expand a recursion. So what have we seen so far? What do we want to still do? We've seen the master theorem. As alternatives, we have recursion trees, we have the substitution method, and for the substitution method, we might need to expand the recursion. Now, naturally, we would be talking about recursion trees next, but to explain recursion trees, let me first explain what it means to expand a recurrence, because recursion trees essentially just means that we're going to expand a certain type of recursion in a nice way. Now, let's have a look at what it means to expand a recurrence by the example of the recurrence of the running time of n factorial. So that was this recurrence. T of n is t of n minus 1 plus theta of 1. So first of all, observe that we can plug in other values than n into this recurrence. So instead of this n here, I can put in other values, and then I just have to replace this n by whatever I plugged in on the left-hand side. So for instance, assuming n is at least 2, we can look at the recurrence where we plug in instead of n minus 1. Now we also have to here replace the n by n minus 1. What does that mean? We get n minus 1, and then this minus 1, plus this term. So n minus 1, that's n minus 2. So t of n minus 1 is t of n minus 2 plus theta of 1. And I can play the same game, assuming that n is large enough, with n minus 2. So t of n minus 2 is t of n minus 3 plus theta of 1. And so on. And so I can plug in different values into the recurrence here. That will give me this different value then also there. So I'm not restricted to using the recurrence simply on n. Having this, we can now substitute t of n minus 1 in this recurrence by the right-hand side of t of n minus 1. So in the recurrence t of n, we can substitute t of n minus 1 by the recurrence for t of n minus 1. So how does that look like? So we have t of n is t of n minus 1 plus theta of 1. We know that this here, t of n minus 1 corresponds to t of n minus 2 plus theta of 1. So we plug that in. What does that give us? It gives us t of n minus 2 plus theta of 1. So that's this part, plus this theta of 1 here. That is that part. We can play the same trick again. So t of n minus 2 is t of n minus 3 plus theta of 1. Plugging that in, we replace this part by that, then we get this here, and then those two remain, which give me this. And so on. And in this way I can make this one here, can reduce n further, or the value that we have there further and further. Eventually we will hit the base case. So here we should now use some kind of, either there's a base case given, then we use that, or we use a meaningful base case of simply theta of 1 and derive the general recurrence. So what we have here is that for every time I go down by 1, I get an extra theta of 1. That means I get lots of these theta of 1s until I hit n is 1, so until I hit t of 1 here. So how many of these do I have? Every time I go down by 1, I get 1 extra, meaning I go down n minus 1 times. This means now that t of n is t of 1 plus n minus 1 times theta of 1. So that is what we have here. T of 1 we assume is theta of 1, so this gives me n times theta of 1, which is theta of n. So now we can use the same idea to solve the recurrence for binary search. So here's the recurrence for binary search. So we have t of n half plus theta of 1. And the first part here is again to observe that instead of having n on the left-hand side, I can have other values on the left-hand side, and then I get other values on the right-hand side. If this replacing n by n half confuses you slightly, then you can also think of this recurrence as having an m here, and the m I can plug in n, then I get the t of n is t of n half plus theta of 1, but I can also plug in n half, and if I plug in n half, so if I set m to n half here, then on the left hand side I get t of n half, on the right hand side I get t of n half divided by 2, so that is t of n quarter plus the theta of 1, and I can continue with this. So for instance, if I plug in n divided by 4, I get t of n divided by 8 plus theta of 1. Now same idea as before, we plug in the recurrence for t of n half into the recurrence of t of n. So how does this look like? It looks as follows. I have t of n is t of n half plus theta of 1, which is, now this corresponds to t of n half, t of n quarter plus theta of 1, plus the theta of 1 that we had previously, so this is still here. And now I continue, t of n quarter, I can plug in the recurrence, so t of n eighth plus theta of 1, which gives me 1 extra theta of 1 here. Eventually I will hit the base case, and when I hit the base case, I'm done. And in that way then I want to derive the general recurrence relation. So what do we have here? We have t of n is, and I do this until, let's say, I hit t of 1, and with each time I divide here by 2, I get 1 term theta of 1. So how often can I divide n by 2 until I reach the base case? So having the base case 1 here, it means that, so every time I divide by 2, I get a term n divided by 2 to the I, in principle even rounded down, but that's not that important here. Now, at what point, so how large does I need to be until this is 1? So this is the same, and again, let's ignore these here, the rounding. This corresponds to n is 2 to the I, which applying logarithms on both sides gives me that log n is I. Meaning that after I iterations of expanding, of log n iterations of expanding, I hit t of 1. Meaning that the number of terms here is actually log n many. So I get theta of 1 plus log n theta of 1s, which is theta of log n. And now we know that binary search runs in theta of log n time. Note that in the binary search, actually, so here we didn't write down the base case. Binary search, we actually stop with n is 0, so then we have to be a bit more careful here. So you shouldn't use a 0 here, because otherwise everything is 0. But there what happens is that indeed the rounding down gets important. That was the binary search recurrence. Now let's assume we take the MergeSort recurrence, here written as 2 times t of n half plus n, so in principle theta of n, but let's just do n here. Now, of course we could do the same idea, so we can plug in n half instead of n, and then we get n quarter, so 2 times n quarter plus n half, and so on. And of course we can substitute t of n half by the recurrence here, so this part. But if we do so, things get a bit messy. Now, because we have 2 times 2 of t of n quarter plus n half plus n. So this can still be done. it's also in this case still fairly doable, but the better way of doing it is using recursion trees. And that's what we're going to look at next. Just a quick quiz before that. What does the following recursion solve to? T of n is T of n half plus n. Does it solve to log n, or n log n? So this recurrence solves to theta of n. So why is that the case? Because we get an n, then we get an n half, then we get n quarter, and so on. So what we have here is a sum I goes from 0 to roughly log n. And now, of course, log n isn't always an integer, so we should be a bit more careful here and round. But if I don't explicitly round, then just think of it rounded, or think of n being a power of 2. So this is n times 1 divided by 2 to the I. Yeah, so n times 1/2, n times 1/4, and so on. So this is the same as n times the sum 1 divided by 2 to the I. It's actually not that important that it wants to log n, because this sum, even when it goes equals from 0 to log n, even if we would go to infinity here, this is a constant. So 1 plus 1/2 plus 1/4 plus 1/8 and so on always stays smaller than 2. And that's why this recurrence solves to theta of n. Let's solve recurrences using recursion trees. And we do this first by this example. T of n is 2 times t of n half plus n. So what is a recursion tree? A recursion tree is simply a systematic way of expanding the recurrence in such a way that we can easily add up the resulting terms. And what we do is the following. So we have the recursive part here, and we have what in the master theorem corresponds to the f of n. So we take this f of n part and we write it at the top of the recursion tree. So that's simply n. Now we still have to handle 2 times t of n half. Instead of taking this as 2 times t of n half, we're going to take it as n half plus t of n half plus t of n half. And why do I rewrite it like this? Because what we're going to do is this tree will have 2 branches, and each of these branches will correspond to a recursion tree for t of n half. Now, I have n, and I have 2 recursion trees for t of n half. If I want to draw a recursion tree for t of n half, the first thing that I do at the top, I put in whatever the term is here. But now the term here is, because we here have n half, is also n half. So what this looks like is the following. We get n half here, and of course recursion trees for t of n quarter below that. So again, expanding those trees further, I get for each of these n half, I get 2 branches, and for each of those branches I get n quarter, and so on. Eventually, on level I, so if this is level 0, level 1, level 2, if I do this up to some I, what I have is I'm going to have divided by 2 to the I. So on level I have n divided by 2 to the I and many of those terms. And I expand further until I hit the base case. And those will give me simply constants. Now the trick with recursion trees is that I'm now going to add up the contributions level by level. Top level, I only have 1 term, it gives me an n. Second level, or level 1, I have 2 terms, n half plus n half, that's 2 times n half, it's actually also n. Next level is 4 times n quarter, it's also n. On level I, how many of these terms do I have? So each time going down, I double the number of terms. So now I have 2 to the I terms of the form n divided by 2 to the I. So that is 2 to the I, n divided by 2 to the I, simply n. Now, how many levels do I have? Each time n is divided by 2. So how large can I get? So on level I, I'm looking at n divided by 2 to the I, and let's say I stop when this is 1. So when is this 1? It's 1 when n is 2 to the I, which is the same as saying that I is log n. So we have log n levels, and of course log n might not be an integer, so you can think of this rounded down, or you can think of n being a power of 2. I will simply write log n. So we have log n levels, each contributing n. Now we should have a separate look at this last level. So there we have these theta of 1 terms. We should think about how many of these do we have. Okay, if this last level is level log n, and every time I went down, I doubled the number of elements, and the number of elements that I have here is 2 to the log n many, meaning I have n terms on this lowest level. That means I have this last level contribute theta of n. Adding all of this up, so n plus n plus n and so on, log n times is simply n times log n, or log n times n, plus the theta of n at the end, meaning that the running time of this recurrence solves to theta of n log n. Let's relate this to the master theorem. So this is a recurrence that could also be handled by the master theorem. So the n here, that's our f of n. We have a is 2, b is 2. So in the master theorem, n to the log a base b, that is n to the log 2 base 2, which is log 2 base 2 is 1, so this corresponds to n to the 1, which has the same growth rate as n. It's the same. So we are in case 2, and in case 2 we get theta of this, or theta of n times log n, which is exactly what we have here. So I would like to give you a little bit of intuition of why this happens in general in the master theorem, which in principle is also the idea behind the proof of at least that case of the master theorem. And for that, you can look at the contribution at level I. So at level I, the number of these terms is a to the I. So every time I go down, the number of terms goes up by a factor a. So if I go down I times, I have a to the I terms. Each of these terms has a form f of n divided by b to the I. Now, if we know that the growth rate of f of n is n to the log a base b, then this corresponds to n divided by b to the I to the log a base b, at least in terms of growth rate. Do the calculation here and use logarithm rules. You will see that we again end up with f of n on level I, meaning we get exactly what we had here. So here we had always n. In the general setting, we always get f of n up to some constant. And we add up all of those f of n terms, so that gives me f of n times number of levels. So now we just need to see why is the number of levels always log of order log n. So the number of levels is how often can I divide n by b until I hit 1. And that is exactly log of n base b. So log of n base b I can again rewrite as log of n divided by log of b. Log of b, if b is a constant, it's also a constant, some number. So this is of order log n. So no matter what b is, as long as b is a fixed number, we get log n levels. Per level, we get f of n. So we get theta of f of n times log n, and that is case 2 of the master theorem. Let's have another recursion and another recursion tree. 2 times t of n half plus n squared. Same idea as before. we take this, what I call now a f of n term, write it on at the top of the tree. We get two trees for t of n half and for t of n half. We plug in the value that we get if we plug in n half in here. So we get n half squared. And then we have subtrees, 4 subtrees for n quarter. We get n quarter squared and so on. In general, we get n divided by 2 to the I squared terms. And this goes down. Now let's add up level by level. First level obviously is n squared. Next level is n divided by 2 squared plus n divided by 2 squared. So that is 2 times n divided by 2 squared, which is 2 times n squared divided by 2 squared, which is n squared divided by 2. We can do the same on the next level. We have 4 times n divided by 4 squared, which is 4 times n squared divided by 4 squared, which is n divided by 4, or n squared divided by 4. The general term that we get here on level I is n squared divided by 2i. And then let's have a look how many terms do we have on the last level. Every time we divide by 2, so we have log n base 2 levels. And we always have a branch out of 2, so the number of terms is 2 to the log n, which is simply n. Yeah, so this is n. I can rewrite this as n to the log 2, and log 2 is 1. So that's n, this last term here. Let's add all of this up. We have n squared plus n squared divided by 2 plus n squared divided by 4, and so on. So you should recognize this as a geometric series. So we have n squared times sum I goes from 0 to log n. 1 divided by 2 to the I. So this is, if I is 0, this is 1. So that's the top level here. If I is 1, this is 1/2. That's here, and so on. Now the geometric series, 1 plus 1/2 plus 1/4, even if it would go further than log n, it always stays below 2. So this is a constant. So overall, we get n squared times a constant, which is order n squared. Let's briefly relate this again to the master theorem. So in terms of the master theorem, the case that we could apply here is case 3. Namely, f of n grows faster than log n to the n to the log a base b plus some epsilon, because a, b are 1, so we have n to the 1, so n to the 1 plus epsilon. This I can take as lower bound on n squared, for instance, if epsilon is 1. In this case, what we get is that we can bound the contributions of the tree by a geometric series like we had it here, in such a way that we get f of n times a geometric series. A geometric series where the term inside, so here we have the term inside that it has a form a to the I, where, not a, let's give it a different name, c to the I, where c in our case is 1/2. So this c here is smaller than 1, and then the geometric series goes to a constant. Every time we are in case 3 of the master theorem, we can actually bound the contributions of the recursion tree by f of n times a geometric series, and that's why the running time overall is of order f of n. That's just a rough intuition of how this relates to the master theorem. Okay, last recursion tree for now. T of n is 4 times t of n half plus n. By now we know how it goes. We take the n, put it on top. Now we have a 4 here as a. So that means we get 4 branches, each of which will correspond to a recursion tree on n half. So we get 4 branches. Each starts with n half. Each has again 4 branches, which then have on the next level n quarter, and so on. Eventually we hit theta of 1. So let's add all of this up. On the top level, obviously n. On the next level, 4 times n half is 2n. Then, on the next level, the number of terms is 4 times 4, so 16 terms. Each of them is n divided by 4, so we get 16 times n divided by 4, 4n. In general, on level I, we will get 2 to the I times n. Now let's have a look at how many elements do I have on the last level. So the number of levels is how often can I divide n by 2? That is log n base 2. The number of elements on level I is 4 to the I. So the number of elements of the last level is 4 to the log n base 2, which I can rewrite as n to the log 4 base 2, which is n squared. So I have n squared elements on the last level, so the last level contributes theta of n squared. Now what I claim is that all of this adds up to order n squared. The reason being is that we again have a geometric series here, but now inside the geometric series we don't have something that is smaller than 1, but what we have, so let me take the n outside, it's n times I goes from 0 to log n, and again let's ignore rounding, 2 to the I. This geometric series, if we go up to log n, gives us 2 to the whatever it goes up to, log n, actually then plus 1, minus 1, divided by 2 minus 1, which is 1. So this is what this evaluates to. Of course we have this factor n still. Now this 2 to the log n is simply n. 2 to the 1 is 2, so we get 2n squared minus 1. So this geometric series has indeed quadratic growth rate. And this is what we would also expect from the master theorem, because from the master theorem we have a is 4, b is 2, log a base b is log 4 base 2 is 2. So we're comparing n squared with f of n, which is n. N squared is clearly bigger, even by at least some epsilon, so we can write f of n is an O of n squared minus epsilon for, let's say, epsilon is 1. So case 1 of the master theorem applies, and we get a running time of n to the log a base b, which is order n squared. To get out an intuition of why the case 1 of the master theorem is what it is again the case that, and this somewhat corresponds to how we will prove the master theorem. If we have this setting, then we can essentially bound this by this geometric series here, in which the last term, you could say the lowest level, is the dominating part, and the lowest level corresponds to the n to the log a base b. So much about recursion trees. Once more, in terms of the relation to the master theorem, in case 1, which we just saw, what we had is that the bottom level of the recursion tree dominates, and that's why we get the number of elements on that bottom level, which is n to the log a base b. In the case 2, we had that essentially every level has the same contribution, and therefore we had to count the number of levels and take the contribution per level. That is log n. That is log n times f of n, or times n to the log a base b. So here all levels contribute, and the final case was the case 3, and there the top level dominates, and therefore at the top level we have that f of n, which also determines what the running time is. So here's a small quiz to wrap up this part, and that is the following. Which of the following expressions does not correspond to the depth of the recursion tree, or for t of n is 9 times t of n divided by 3 plus n squared? Log n base 2, log n base 3, or theta of log n. So the expression that does not match here is the log n base 2. Because here what we have, every time we go down a level, we divide n by 3. How often can we do this? Log n base 3 times. So we get this term here, b. Now, of course, log n base 3 is the same as log n divided by log 3. So alternatively, we can simply look at this as being theta of log n. So C is also fine as answer. A is not. Finally, we have the substitution method. So once more, where are we standing now? We have the master theorem. We have recursion trees. We have seen what it means to expand a recursion. Now, if the master theorem doesn't apply, and if we don't quite can pin down the running time using a recursion tree, then as a last resort, we can try to simply write down what we think the recursion is and prove that it's actually the right answer by using induction. So this you will only want to do if all other options fail, but then it's a completely valid and correct way of solving a recursion. So let's do this by example. So let's say my recursion, and now we actually also need to more carefully take the base case into account. Let's say this is my recursion, t of n is 2 times t of n half plus n, or 2 in the case of n is 1. Now we claim that this solves to order n log n. And of course, by now we know that this will solve to order n log n because this is simply the MergeSort recurrence. Putting that aside, we now will prove this by induction. And that's actually a bit trickier than you might think. So we do a proof by induction. So what we want to show, if I want to show t of n is an O of n log n, what I want to show that I can find an n0 and I can find a c such that I can bound t of n by c times n log n for all n larger equal n0. So how should I pick my n0? Often enough we pick n is 1, but n is 1 is not a good choice here, and the reason being is the log n. So if n would be 1, t of 1 is 2, but log of 1 is 0. So this will be simply 0, so I cannot bound 2 by c1 times 0, no matter what c1 is, obviously. This does not work. So I will have to start with, let's say, n0 being 2. I could also do a larger one, but that just makes our life more difficult. Now, that means we will be taking 2 as a base case. But here life is actually even more difficult because 2 as a base case is not quite sufficient. So why do we need additional base cases? For the following reason. What we want to have in an induction is either we have a base case or we have a case that reduces to a case for which the induction hypothesis holds. So, and for the case of 3, if I would want to use induction hypothesis for 3, then I would have to have that we know that the property that the induction hypothesis holds for 3 divided by 2 rounded down, because that is what we have here. But 3 divided by 2 rounded down is 1, and n is 1 is actually a case that we're excluding. We're starting with n0 as 2. So that means we also need 3 as a base case. In contrast, 4 divided by 2 is 2. So in that case, for 4, we already have a case that is in the set of numbers larger equal n0. So that is handled by a base case. So in short, what we need is we need to have 2 and 3 as a base case here. T of 2, I can simply plug in. I get 2 times t of 1 plus 2. This gives me 6. I want this to be bounded by c times 2 log 2. Log 2 is 1, so c times 2. If I pick c is 3, I will be fine. If I pick c even larger, I'm also fine. N is 3. T of 3 is 2 times, now here, if I plug in 3 divided by 2 rounded down is 1. 2 times t of 1 plus 3, it's, okay, 2 times 2 plus 3 is 7. This should be smaller equal c times 3 log 3. Okay, if you do the calculation, that also works with c is 3. Now we have the base cases handled. We've also picked c and n0. Now we do the inductive step. We start with a general n. We assume it holds for n half rounded. The induction hypothesis holds for n half rounded down. So we can plug in this here, which will be our induction hypothesis, for n half rounded down. So I get 2 times c n half log n half. In principle, I should round down, but as an upper bound, I can omit the rounding down, plus n. Now, what do we have? We have a 2 here, we have a 2 here. We have Cn log n divided by 2. So let's rewrite that. Cn log n divided by 2 is log n minus log of 2, which is log n minus 1. So now we have Cn times log n minus 1 plus n. So this I can bound by c times n log n, because what we have? We have c times n log n minus c times n plus n, and because c was 3, this term is negative, so this is an upper bound. Okay, that was an example of a substitution method. We won't need to use that anytime soon again, so that's why I'm also not giving any more examples of that. In general, when we analyze the running time of an algorithm, so for recursive algorithms, if possible, we use the master theorem. If not, recursion trees. And if not, substitution method. Again, if we don't have a recursive algorithm, or if our algorithm features a loop, what we do is we simply add up terms, and for a loop it simply means that we do a summation. For that, it's useful to, so for the recurrences and for the summations, it's good to know some common sums and recurrences. So a common recurrence is a MergeSort recurrence, a 2 times c of n half plus theta of n. It's good to know that that solves to n log n, or theta of n log n. Then also, if instead of the sum of I, we have the sum of I squared, then simply on the right hand side, the exponent also goes up by 1, so that would be theta of n cubed. So that's what we've seen in this video: master theorem, recursion trees, expanding a recursion, and substitution method. So let's wrap up this video by a quiz, or more specifically actually by a problem that I just want to state, and you can try to solve it. And that is, what is the running time of the following sorting algorithm? So what does this algorithm do? It takes the first half of the array, recursively sorts it. It takes the second half of the array, recursively sorts it. Now that is very much like MergeSort, but MergeSort now would merge those two parts. Instead, what we do is we take the middle half, so ignore the first quarter, ignore the last quarter, sort that. Okay, that as such is not a valid sorting algorithm, so let's do the same again. Sort the first half, sort the second half, sort the middle half. That's exactly what happens here. So you can think about A, why does this actually sort? And B, what is the recurrence and what does the recurrence solve to? The reason I give this example here is that very often we get recurrences of the type either where A is B or where A is 1. So here I wanted to show you an example of an algorithm where actually A and B are not the same and also A is not 1. Okay, enjoy solving that. Until next time.